Hi everyone, Mr. Lee here. In this video, we're going to go over derivatives. And it's just a very introductory idea to derivatives. I'm going to show you how to take derivatives. I'm going to also show you the shortcuts. Now, just so you know, when you take calculus and your calculus teacher teaches about derivatives, they will go a little bit more in depth. They'll give you all the more advanced tools that you can use when doing the derivatives. Now, for the sake of our class, in order to survive the first couple of units, I'm just going to show you the very basics of derivatives, and that will be enough for us. All right, now I'm not going to go into the meaning behind the derivatives, the concept behind derivatives, because what I want to do is when we go into each and every single unit, I want to show you how this tool of finding the derivative of a function actually applies to the unit itself. I want to give you the meaning behind this powerful tool, and that tool is called taking the derivative of a function. All right, now before we begin, let's do a couple of definitions. So the first definition is the definition of a function. Now, oftentimes in math class, we will see function written as f of x. Now, sometimes you might see g of x or h of x. All right, so there's a lot of different letters that we can put in front of it, but usually f of x is how we write function. Now, for us here in physics, functions have a very specific meaning. Functions tells us the relationship between two variables. Okay, so for example, let's say I am outside and I'm walking, walking through my neighborhood, and I want to know how, if I walk for, let's say, 30 seconds, where will I be? What is my location? Okay, so here my two variables is, the first one is called position, right? So I want to see where I end up, and my second variable is time. So we usually represent position with the letter x, and we usually represent time with the letter t. Now, don't be confused. This x for position and this x up here, they're not the same. X is position here, where x up there is a independent variable. It's not the same. X is just like a placeholder. Right? So if I were to create a function for this, I could create something like this. So my position with respect to time is given by this equation. I don't know, let's say it's 7t, right? Where 7 is just a constant, and this constant is just helping us describe the scenario, where t, okay, this is my variable, and more specifically, this is my independent variable. And here, x, this is my dependent variable. And once again, this t is my, my independent variable. So what this function is telling me is if I walk for 30 seconds, so t will be 30 seconds, I will have a location of x, right? So let's try this. So if I were to put in 30 for t, x of t is equal to 7 times 30, we will get a position of 210. So x of t would give me 210 in meters for my units. Okay, so something very simple. So this is just to show you how functions work. It's an equation, but that equation tells us how two variables relate to each other. All right, now for the actual derivative portion. So there are going to be two rules that we're going to cover. One is called the power rule and one is called the constant rule. I want to go over the constant rule first because I think it's just the simplest rule, a constant rule. So the constant rule tells us if you take the derivative of a constant, you will get 0 as the derivative. Now, once again, your calculus teacher will go into why this is the case and have a more formal definition. But for the sake of our class and for just being able to get through the ideas and the problems, this is the rule that we will abide by. All right, so how is this really applied to us? Let's do some examples. So I'm going to give us a couple of functions where we have just a constant. So let's say we have f of x is equal to 7. So if I were to take a derivative, I'm going to show you the different notations. Okay, so the first one is something that you'll probably do in your calculus class, where we just put apostrophe, okay, after the dependent variable. So f prime of x is equal to 0. So in this notation, this is showing us that we just took the first derivative of this function. We took one derivative of it. So for example, if I did it like that, okay, that means I took two derivatives. But we'll worry about that later. Okay, so this is the first derivative. And because 7, the number 7 is a constant, okay, there is no independent variable, okay, independent variable attached to that 7, we can consider that to be a constant. All right, so I'll show you another one. Let's do v sub t is equal to 25. Okay, v sub t is 25. Now I'm going to show you a different way of writing the derivative. So I'm going to show you the first way that I just showed you before. So v prime of t is equal to 0, right? Because 25 is a constant, there is no t attached to that 25, therefore it is a constant, and so the derivative will be a 0. Well, we can also write it like this, dv dt. The derivative of v with respect to t is equal to 0. So this is another way of writing the above. So this is the same thing. Okay, we can write it in one way or another. And you'll often see me switch back and forth between the two. But just so you know, you can write it the first way or the second way. All right, now another one that I want to show you, let's say we have, I don't know, omega theta is equal to pi. Right? So here I chose Greek letters because I want to kind of throw you off, right? We see that this pi, okay, which we know is to be a constant, doesn't have the independent variable pi attached to it, right? We don't have anything like this. And so because that is the case, this pi is a constant, and we can write it as omega prime is equal to 0, or we can write it like this, the omega d theta equals 0. Okay, once again, this is the same thing. All right, so that's the constant rule. If you have a constant, the derivative of the constant will be 0. All right, now let's do the power rule. Now this is where things get fun. So the power rule. Now I'm going to show you the official equation for the power rule, and then I'm going to show you how we can apply that equation, and then after that I will show you the shortcut. All right, so we say f prime of x, so the derivative of the function is equal to n, which is a number, which is a constant, x, which is the independent variable, okay, and then n minus 1, where this n is the exponent. All right, so I want to break this down. If I were to have a function f of x, oh boy, why did that turn into a trapezoid? There we go, is equal to, let's say, 5. Now let's get rid of that 5. x3. Okay. All right. So if I were to take a derivative of this function, f prime of x, so I want to make this function, I want to take the derivative of it, and I'm going to use this format. So this n, okay, is my exponent. So this is my exponent. And in front of the independent variable, so here's my independent variable, I'm going to pull this n to the front. So we get 3. This is x, so we're not going to mess around with that, but we have n minus 1. So n is 3 minus 1. So what we end up with is 3x2. That's my derivative. All right, let's try another one. So let's see if we have v sub t is equal to x, or excuse me, that should be at to the 4th. All right, so if I were to take the derivative, right, we want to bring this exponent down to the front, 4, okay, and we see that here, right, this is the exponent n, and we're bringing it down to the front. The independent variable, which is t, and then 4 minus 1, and so what this ends up, dv dt, is 4t to the 3rd, and this is my final answer. All right, now let's get a little bit more tricky. So let's stick with the v's and the t's. I'm liking that. V sub t, instead of saying t to the 4th, let's say it's 4t 4t squared. 4t squared. Okay, so if I were to take the derivative of this, now see what happens here. There's something new here. We have this 4. We have this constant. So what we want to do is we want to keep that there. Okay, 4. We don't want to mess with it. There's nothing that happens with that 4. But then we do the derivative or the power rule where we bring 2 to the front. So times 2t to minus 1. So we get 4 times 2, which is 8 t to minus 1. And this simplifies down to 8 t to the first power, which is just 8t. dv dt. All right, let's try another one. Let's try, let's see, a sub v. Okay, let's do a sub v. And let's make it 5v to the 4th. All right, so if we were to apply the power rule, a prime v, so we bring 4 out to the front, right? And then here we have the original, so that's, oops, 4 times 5v. Okay, and this v is 4 minus 1. So 4 times 5 gives us 20, v to the 3rd. All right, so by now you should be picking up on the shortcuts. Okay, so you don't have to always, you don't have to be memorizing this form of the equation. The rule simply is you take your exponent and you multiply it to the constant in the front, and you just reduce the exponent by 1. So that's it for the power rule. It can get a little bit more complicated, and we'll do a couple more examples so that you can see that. So let's try a sub t is equal to, let's do 5t to the 4th minus 3. Oops, that should be a t. Excuse me. Why did I write an x? 5t to the 4th minus 3t to the 3rd plus 12t squared, and we'll do plus 75. All right, so here's our function. It's a pretty big function, but if we were to take the derivative of this function, we would write it like this. Let's do dA dt. All right, 4 times 5 gives us 20. 4 minus 1 gives us 3. Minus 3 times 3 gives us 9. 3 minus 1 is 2. Plus 2 times 12 gives us 24. 2 minus 1 gives us 1, so we can just leave it like that. Plus, this is the 75 is a constant, so that'll be a 0. So our equation would just turn out to be like this. Okay, and it's a pretty beautiful equation. All right, let's try one more, and then we'll call it the end of the video. Let's do VT. All right, so let's say we got VT is 9/4, t to the 4, minus 2t plus 16. Okay, so this is the first time we dealt with fractions, and so I do want to take my time to go through this for all of you. dv dt, my first derivative. So we have 9/4 t to the 4. So 9/4 times 4. Okay, 9/4 times 4. Okay, this will just because this 4 is in the numerator and this 4 is in the denominator, it'll cancel out. T to the 3rd minus 2. Okay, there, because we have a 1 there, so 1 times 2 gives us 2, and 1 minus 1 gives us 0. So a variable to the 0th power is just 1. So I'm just going to leave this as 2 plus 0. Okay, and so we can clean this up to be 9t to the 3rd minus 2 dv dt. All right, so this is my first variable, or my first derivative. All right, so that is how you do derivatives. Now, the only other thing that I want to touch upon is if you have to take two derivatives at once, and we'll do a quick little function so that we can take a look at that. So if we have f of x is equal to, let's say, 3x to the 3rd, we'll keep it simple. All right, plus 2x squared, the first derivative, f prime of x, 3 times 3 gives us 9. X 3 minus 1 is 2. 2 times 2 is 4. X 2 minus 1 is 1, so I'm just going to leave it like that. So this will be the first derivative. Okay, so if I want to do another derivative, we'll do f double prime of x is equal to 2 times 9, which is 18. X 2 minus 1 is 1. X to the first power is just x. Plus here we have, remember, there's secretly a 1 there. 1 times 4 is 4. And then we have 1 minus 1 gives us 0, and any variable to the 0th power will give us 1, so this is secretly 4 times 1, and so I'm just going to leave that as a 4. So this will be our second derivative, and we're going to do it one more time. Let's try it. To the third variable, or to the third derivative, 18x, so we have x to the 1, 1 times 18 just gives us 18, x to the 1 minus 1, so x to the 0 is just 1, so 18 times 1, I'm going to leave it as 18, and here we have a constant, so that constant will give us 0, and so we get the third derivative to be 18. Alright, so here we have the 3 derivatives of a single function. Alright, that's it for me for now. Once again, this is just a very powerful tool, and when we go deeper into the physics unit, we'll see exactly how we can apply the derivatives into the units and what it can do for us. All right, until next time, bye-bye.